Section 1.2 is on fractions in algebra, and so we're going to start by looking at objective 1, converting between mixed numbers and improper fractions. Part of the reason we want to do that is because anytime we're using fractions in algebra, we're going to want them to be improper fractions, and we're not going to use mixed numbers. Mixed numbers are still useful. We'll see them in application problems or maybe as a final answer sometimes, but especially in algebra, I'm going to be using improper fractions. So, if I have a mixed number that I need to convert to an improper fraction, the first step is to multiply the denominator by the whole or natural number. So 7 right here times 5 right there will be 35, plus the 3 that's already in the numerator over the original denominator. Okay? So multiply the denominator by the natural number, and the natural number is just the whole number part of it. And then add the numerator. Okay? And then the final answer for this improper fraction, so 7 times 5 is 35 plus 3 is 38 fifths. Okay, and that's my improper fraction. If I can convert something to an improper fraction, I'm going to have to also know how to convert something from an improper fraction back to a mixed number. Like I said, in algebra, we're not going to be using mixed numbers, but we may still need to answer a question as a mixed number if it's a story problem or if it's something where a mixed number will make more sense. So 76 ninths, I'm going to use long division right here to convert this into a improper fraction into a mixed number. So I'm going to start with 9 goes into 7 0 times, 9 goes into 76 8 times. That's 72, so when I subtract them, I'm left with 4. We went 8 whole times with 4 left over. So this would be the mixed number 8 and 4 left out of 9. Okay, so that's the mixed number. So I divide the denominator into the numerator, record the quotient, that's the result of the division, as the whole number, and the remainder. The remainder is the numerator of the new fraction. So my quotient, my remainder, 8 whole times went in, 4 left over, so 8 and 4 ninths. It's still ninths, it was always ninths. The denominator will not change. For the next objective, we're going to write the prime factorization of a composite number. The first definition is a prime number is a natural number greater than 1 whose only factors are 1 and itself. So, for examples, we're going to list the first 10 prime numbers. 1 is actually not considered prime. The first prime number is 2. 3 is also prime. 4 is not prime. 2 goes into it. But 5 is prime. 7 is prime. 9 is not prime. I'm skipping all of the evens because they're not going to be prime since 2 goes into them. 11 is prime. 13 is prime. 17 is prime. 1, 2, 3, 4, 5, 6, 7. So I need 3 more. 17. 19 is also prime. 21 is not. 23 is. 25 is not. 27 is not. 29 is prime. I think I got more than enough right there. Okay. It's useful to know the first several primes, the first 10 primes, or at least the first up until 20. However many that was, 1, 2, 3, 4, 5, 6, 7, 8, the first 8 primes up until 20, because we're going to need them if we factor numbers, factor large numbers especially, we might need the first 8 primes or so. Okay. If a number is not prime, then it's composite, so a composite number is a natural number greater than 1 that is not prime, and expressing a composite number as a product of primes is called factoring it. Let me read that again. Expressing a composite number as a product of primes is called, no, the process is called factoring, I guess. It's called the prime factorization, would be another way of saying it. To find the prime factorization of a factor, so I've written the verb form of it instead of the noun form of the word. Same difference. Don't tell your English teacher. So, I want to factor 240. One of the ways I'm going to do this, I'm just going to write down 240. And I'm going to say that it's equal to, I'm going to make a list right here, a chain of numbers that multiply to 240. Since it ends in 0, I'm going to start with 24 and 10. I know that 24 times 10 is 240. Anything times 10 will just add a 0 to it. Then I'm going to break this up again into smaller numbers. I'm going to break the 24 up and the 10 up. 24, we'll go sideways because I need more space. 24 is 4 times 6. And 10 is 5 times 2. I'm going to break each of these numbers down until it's prime. 5 and 2 are already prime, so I don't need to break those down any further, but 4 and 6 are not, so I'm going to keep going. 4 is 2 times 2 times 6 is 3 times 2 times the 5 times the 2. Okay? And these are all prime now, so just to finalize this or finish it off, I'm going to write them in order. So 2 times 2 times 2 times 2, there were 4 different 2's here, times 3 times 5. That would be the prime factorization of 240. It's also okay to write that in exponent notation. If you wanted to write it as 2 to the 4th times 3 times 5, it's just the exponent notation of the same thing. 2 times 2 times 2 times 2 is 2 to the 4th times 3 times 5. Okay. Objective 3, reduce or simplify fractions. So we want to reduce these fractions to their lowest terms. Sometimes it's useful to find the prime factorization of each of the numbers, especially for the numbers that are very large. But sometimes it's even faster just to look at the two numbers and divide them both by a number that goes into them. For example, on part B, I can do that quickly because I can see that 35 and 50 can both be divided by 5. So without completely factoring them, I know that I can divide them both by 5 because one ends in a 5, one ends in a 0. And that's going to allow me to simplify it a little bit. And once I simplify it a little bit, I'll be able to see if there's any more I can do. Once I divide them by 5, I get 7/10. Since those numbers are a lot smaller, I know that 7 is prime, and there's no number that goes into both 7 and 10 besides 1. So that would be reduced. Okay. It's not always possible to do that, though. So let's look at the prime factorization method for part A. The prime factorization method would say, okay, split up 42. So that's 7 times 6. And actually 6 can be broken down further. So let's make that 7 times 3 times 2. So that's the prime factorization now of 42 over 15, which is 3 times 5. Now we're going to say, okay, I'm going to divide them both by 3 since I had a 3 as a common factor. Put the pieces back together, and that's going to leave us with 14/5. So the method that I prefer to use most of the time is to divide by a common factor. I think that it saves me a little bit of time over factoring something all the way down, but it might require a little bit more trial and error than factoring something all the way down does. So whatever you choose is up to you. Let's go ahead and look at the 120 over 86 example. Again, I don't know what the biggest number that goes into both of those is right now, but I'm just going to start by dividing them both by 2, then I'm going to keep going and keep going until I'm done. So 120 divided by 2 is 60. 86 divided by 2 is 43. Now, I'm not totally sure about 43, what goes into 43, so I'm going to check. 43 divided by 3 doesn't work. 43 divided by, I don't need to try 5. I don't need to try any even number because it's not even. I know 7 doesn't work, but we can try 7. And once I tried 7, I noticed that the number I got back was smaller than 7, which meant there was no number that went into 43 between 7, or bigger than 7, because I would get smaller numbers in return. So I tried everything, all possible primes, so I know that 43 is prime. So this is done. Okay. I should definitely make sure that I am confident there's no number that goes into the bowl before I say it's reduced. It's a good idea to check to see if you can make that, if it's either prime or if you can make sure that you can find all numbers that go into it. Okay, and the next one. And then we start by dividing them by 2 because they're both even. I know I can divide them both by 2. So 144 divided by 2 is 72 over 324 divided by 4 is 162. It's still even, so I'm going to divide them by 2 again. Okay, so that'll give me 36 over 81. Alright, they're not even anymore. This 81 isn't. but they're smaller, so I know that 3 goes into 81 and 3 goes into 36. Let's divide them by 3. 3 goes into 36 12 times. 3 goes into 81 27 times. I can still divide them by 3. So that would give me 4 over 9. And I know that's finally done because the only thing that goes into 4 is 2 and 2, and 2 and 2 don't go into 9. So I'm done. Okay. So again, I took this one step by step. I divided by 2, then 2 again, then 3, then 3. I had to do 4 different divisions here to get this reduced. If I wanted to do it faster, I could have tried bigger numbers. For example, 2 times 2 is 4 times 3 is 12 times 3 is 36. So 36 actually would go into both of those if we check. 144 divided by 36 is 4, and 324 divided by 36 is 9. So if I would have divided them both by 36, I would have been done, but I didn't know, looking at the problem, that 36 went into it, so I went with those smaller pieces that I could see. Alright, let's try the next example. The next objective is multiplying fractions. Multiplying fractions works straight across. When I multiply two fractions together, I multiply the numerators and I multiply the denominators. So for the product of the numerators divided by the product of the denominators. And I always reduce wherever possible. I actually make reducing my priority and I do it first. For example, 14 and 21 can both be reduced by 7. If you divide them by 7, you're going to be left with 14 divided by 7 is 2, 21 divided by 7 is 3. 8 and 10 can both be reduced by 2, leaving me with 5/4. So the answer here, multiplying across the top, what's left, oops, I found one more reducer I could do. This 2 can be reduced with this 4 by dividing them both by 2. So I can reduce any top with any bottom. My final answer on this one is going to be 1 times 5 is 5 over 2 times 3 is 6. By reducing first, I'm assured that I have my answer in lowest terms when I'm done, and reducing first is often easier because the numbers are smaller. Okay, so look at the next one. Alright, the next one is 2 mixed numbers. Mixed numbers cannot be multiplied. These must be turned into improper fractions. Okay, so let's make them improper. So 4 times 3 is 12, plus 3 is 15/4, times 1 times 5 is 5, plus 3 is 8/5. So let's reduce. 4 goes into 4 once, 4 goes into 8 twice, 5 goes into 5 once, 5 goes into 15 3 times. So I have 3 times 2 is 6, 1 times 1 is 1, 6 over 1 is not simplified because 1 does go into 6 times. So my final answer on this one is 6. Okay. When I'm dividing fractions, I'm going to multiply the first fraction by the reciprocal of the second fraction. Okay, so one of the other ways of saying it is I copy the first fraction, change the sign, and flip the second fraction. So this is 45/16 times 8/35. Okay, we've changed it from division to multiplication by flipping the second fraction. So now the rest of it works just like multiplication. I'm going to find a common number that I can divide both any top and any bottom with. For example, I can divide these by 5. 45 divided by 5 is 9. 35 divided by 5 is 7. And I can divide these both by 8. 8 divides into 8 once, into 16 twice. So my final answer on this one is 9 times 1 is 9, over 2 times 7 is 14. And the last one here, this is again mixed numbers. I can't work with mixed numbers. I must make them improper. So let's do that. 6 times 5 is 30, plus 3 is 33/5. Divided by 1 times 10 is 10, plus 1 is 11/10. Now we're going to change it to a multiplication problem. So this is going to be 33/5. Always copy the first one, flip the second one. Times 10/11. And let's cancel. We can divide those both by 11, leaving us 3 and 1. We can divide these both by 5, leaving us 1 and 2. So the answer on this one is 3 times 2 is 6, over 1 times 1 is 1, or again we get 6.